natural convection. But let me start go because we need some time to have enough practice. And that's the case that we are dealing with radiation. Radiation is, I'm sure we have covered that one in building science. Therefore, you have some good idea about the problem. I'm sure you remember view factor. I'm sure you remember emissivity, transmissivity, and so on. But here we are going to review it one more time and integrate some a little bit more information. The objective here is classify electromagnetic radiation and identify thermal radiation. We mentioned that when we're dealing with radiation, it covers a wide range of processes, okay? And portion of that part is dealing with thermal radiation. We have some idea what the black body means. We mentioned this is an ideal, a base. We can consider a system is a black body that we can capture all radiation counts, okay? And then emit all of them. It's not the government, doesn't keep anything for himself. There's no tax. Whatever energy comes, take it and give it back everything to the system, okay? And from there, we were able to find the total radiation exchange, okay? Therefore, this is the concept that we are using, the black body. This is the terminology we use it over there to identify an ideal system, okay? Then we look at, again, calculate the fraction radiation emitted in a specified wavelength. As I mentioned, then if you remember building science, emission comes from wavelength of 0 all the way to infinity. Therefore, there's a portion that end up in the thermal radiation, and depend on the back and problem that we are interested. Again, we are interested only as portion of that thermal radiation. We can focus on shortwave radiation. We can focus on red, infrared. We can focus on ultraviolet. Depend on the design of the system that we would like to do. For example, if I want to design a window, only fraction portion of radiation comes in. Therefore, I can select my material that only accept that wavelength. And this is very important when we are designing solar collector, because we would like to calculate the maximum radiation, maximum radiation. And you will see it from that graph, which part is contributing more. And understand the radiation intensity. Again, these are the terminology. We are going to see what that means, radiation intensity, and define spectral directional quantities. Again, these are the question come from different direction. Therefore, we have to focus at that part and develop a clear understanding of the properties of emissivity, absorptivity. These are properties that the same thing that we have for material. When we talk about the density, we're talking specific heat. Therefore, here also these are important parameter of the material that we needed to when we're trying to study radiation, because sometimes we would like to absorb the maximum radiation in the case of solar collector. Sometimes I want to reflect maximum energy in the case of the window if I don't want any energy from sun comes to the building. And sometimes I would like to have a very clear window that is transmissivity. Therefore, for example, these are an example that you have to pay attention to characteristic of the material that we are interested, okay? Then we have applied Kirchhoff law. And of course, I'm sure you remember Kirchhoff. That was the course in your electricity, summation of the current comes to point 0. We use that one, that definition, and that means summation of energy comes to that point. And we're trying to find the absorptivity of surface when emissivity is known. Therefore, we can see the relationship between emissivity and absorptivity, okay? Then that you have seen it in building science. And again, model the atmospheric radiation by use of an effective sky temperature. Therefore, we mentioned, for example, the amount today solar energy is that much. Therefore, we can use that amount of energy. We mentioned, yes, we have a source at a certain temperature that provide the same amount of energy that the sun is providing, okay? Therefore, we are going to discuss it. And one of the important here is, these days we are talking about greenhouse effect. Therefore, what do we mean? How this radiation has to do with greenhouse effect? Okay, these are the points that we're going to cover this part, okay? Okay, again, I'm sure by now you're sick. hearing again conduction and convection, but again, I reminded again, here when we need a conduction, we need a material, we need a solid material, we need a liquid or gases that is stationary. In that case, the heat transfer is by conduction. When it starts to move, we are dealing with convection. Therefore, in both cases, we need a medium here. We need a material, okay, into that. But in the case of radiation, you do not need. Therefore, radiation takes place in even vacuum, okay? Therefore, in that case, we do not need, because the photon is moving. Therefore, in that case, we do not need anything, any medium, okay? As I mentioned, we are talking about electromagnetic wave or electronic radiation. It's covered a wide range. When we are talking electromagnetic wave, it covers a wide range, and a portion of that is thermal. It covers your UV, Wi-Fi, it's dealing with satellite and so on, that sending a signal and so on. Therefore, it covers a wide range radio frequency that, for example, radar, all of them are electromagnetic wave. But a portion of that, part of it has dealing with thermal radiation. In that case, we have what we are discussing with electromagnetic wave we can characterize it based either on the wavelength or the frequency, and the relation between them is this. Okay, if we have wavelength is equal to the velocity, the speed divided by the frequency. Okay, therefore here this expression that we have. Therefore, electromagnetic wave are characterized by the frequency or wavelength. Therefore, when we are talking radiation, we're focusing mainly on wavelength. Ultraviolet in this range, infrared in this range. Okay, therefore we are specifying based on that wavelength that is discussing. Okay, please stop me whenever you need it, whenever you have a question, and I'm going with a mild speed. If you would like to take a note, let me know. Okay, and everything is in your textbook. As I mentioned here, you can see here, this is wavelength, micrometer, and it's covered from 10 to minus 9 micrometer all the way to 10 plus 10, okay? And if you look at here, all of them are dealing with electromagnetic wave. Cosmetic ray is one of them. X-ray is another one, okay? Gamma ray, X-ray, this is we call it, comes from radon, okay? X-ray, that whenever you go on the dentist and so on, they use electromagnetic wave to do X-ray. Then we have ultraviolet here, okay? Then we have a visible range that help us to see the thing, okay? And here is thermal radiation. Therefore, this range that you can see in the blue is referring to thermal radiation. It's sort of from here all the way to here. This is the one we are dealing with when we are talking about building thermal analysis, because all of them are contributing to the heat energy that we have. This is the thermal radiation. Then you have microwave. Look at here. This is the part. And here is radio and TV. And you have electrical power and so on. Therefore, all of them, we are talking electromagnetic wave. Therefore, thermal radiation that we see here is also portion of this part, okay? Portion of this part. Therefore, engineering application concerning electromagnetic radiation cover a wide range of wavelength, as you said here. Look at here, with 10 to minus 9 to 10 plus, okay? Of particular interest in the study of heat transfer, we're dealing with thermal radiation. And this is range of the blue that you can see, this is the thermal radiation, okay? Emitted as a result of energy transition of molecule, atom, and electron of substance. Therefore, these are based on movement of this one. Okay. Temperature is a measure of the strength of this activity at the microscopic level. Therefore, how effective is thermal radiation is a function of the temperature, and we will see it shortly. As the temperature will increase, the radiation will increase. Okay. Therefore, this is something should keep understand the physics of it. Temperature is a measure of strength of this activity at the microscopic level. Okay, as we increase the temperature, this movement, the molecule will become faster, and therefore the energy emitted will become faster. Thermal radiation is defined as a spectrum. Again, as I mentioned, I'm talking about this blue part that you can see in the here, a slide here. from 0.1, here is 10 to minus 1, this is 0.1, all the way to 100. This range, when we are talking about thermal radiation, this is those radiation in the wavelength between the range of 0.1 and 100. This representing thermal radiation. We don't consider X-ray, we are not gamma ray, cosmetic ray, and so on. No, we are talking about this part. This is the part we are interested in design of building engineering. Okay, these are that we are dealing in this aspect. These are the concern of the people in electrical engineering. And here again, we're talking cosmetic ray. This is completely every day we are bombarded from cosmetic, but most of them are passing through the atmosphere and be trapped. And we see here is gamma ray here and X-ray in this part. That as we go up there to the sky, there's this high level. This was for a while the danger to the pilot because they were exposing because at higher level exposed to this X-ray that we are talking gamma ray. Okay. Again, something that we are going to simplify in our application. In our application, here we assume the energy emitted by the body is uniform. In reality is like that. In one direction is more than the other direction. In reality, this is the phase. But to simplify the problem that we are dealing in this study, in our course, we are assuming uniform. Therefore, is not a function of the angle. Is everywhere is uniform. This is the definition of black body, and we assume this is uniform, diffuse all over. If the sunshine comes here, hits the ground, diffuse all over uniformly. Okay. Again, these are the number of simplifications that we make in order to be able to solve the problem. For a body at the thermodynamic or absolute temperature above zero emit radiation in all directions over a wide range of wavelength. Okay, and okay, any point here? The amount of radiation emitted from a surface at a given wavelength depends on the material of the body and condition of its surface, the surface temperature. Okay, therefore this we assume again is material of the body and condition of the surface. We are coming back later on to bring back the issue of emissivity. Okay, but at this moment we assume it's uniform, all of them in the same direction, and so on. A black body, again, keep in mind when we use the black body in the heat transfer here is a body that absorbs the maximum radiation and emit maximum. The maximum amount of radiation that can be emitted by a surface at a given temperature. Therefore, there is no storage here. There is no interest, inflation here. Whatever energy received by that surface, it means whatever energy received by that surface cause the temperature of the body will increase. As the temperature increases, emit all the energy to that environment. Okay, there is no hard and storage capacity here. At a specific temperature and wavelength, no surface can emit more energy than a black body. That's exactly supporting here. You mentioned, look at here, it's mentioned the maximum amount. Maximum amount is exactly here. At a given specified temperature, for example, at temperature of 300 degrees, at the temperature of human body, my body, and wavelength, no surface can emit more energy than a black body. Again, the black body here is only a definition. Okay, it's in my reference point. This is something that a black body absorbs all the energy regardless of the wavelength. For these two statements supporting here. It absorbs all the energy and emit all the energy back. Okay. Any question, please? A black body emits radiation uniform in all directions. That's exactly the point here. Okay. Therefore, now this again, I know you have seen some of this material before in building science, but this is just again repeating that information. Hopefully, we can go faster in this chapter.
Sir?
Yes, sir.
So if we consider the black body at a certain temperature will emit a certain amount of radiation.
Not the maximum.
Yes, maximum amount of radiation. But what I'm asking is if it already have radiation, and then if we add more radiation on that body, the total amount of radiation that the black body
What I'm trying to get here is
emits is both or not.
what I'm trying to get here is that if you have two bodies, two systems at the same temperature, two systems A and B at the same temperature, if A is a black body and B is a normal body or real body, system A provide maximum radiation. Okay, we will see later on, we call it real material, and that's the case. Therefore, this is my reference point. This is something that this is the maximum amount of energy can come out of the system.
Okay.
Good, sir. As I mentioned, that trying to visualize what that means, that going back to the question that you asked, sir, is look at here, I have a cavity here, okay? If a certain ray of radiation comes in and goes, by the time goes, trying to go back, comes here, hit here, reflect back here, absorb, reflect back here, come back here. By the time goes out, is no energy left. And all those energy causes the temperature of this black body increase. And that's the maximum temperature can get, okay? Therefore, trying to visualize what that point means. And we mentioned the total energy emitted by a black body is proportional to the temperature to power 4. Therefore, this is the maximum amount of energy, okay? Again, all of this equation, as you see about conduction, about the convection, come based on experimental. They realize the energy is proportional to the temperature to power 4. Again, this, remember, this temperature is in Kelvin. Remember from now on, we are using this equation, this temperature has to be in Kelvin, not in centigrade. Therefore, we remember this equation was called a Stephan-Boltzmann equation. Therefore, we have a Fourier equation of conduction, Newton cooling law for convection, and now we have another expression that for radiation, and called the Stephan-Boltzmann law. Okay, and the Stephan-Boltzmann law mentioned the energy emitted by a black body is proportional to the temperature to power 4, and proportionality become equal by considering this constant. This is called a Stephan-Boltzmann constant. Okay. Therefore, example, as I mentioned here, is black body again is not the color what we can see it. For example, if white paint can be considered a black body, we can design something that looks white but can emit all the energy back. Okay, these are something we have to keep in mind. It's not, we are not referring to the virtual color that we're talking. If you look at this equation gives you the total energy. But this equation originally was written for a wavelength at any wavelength and at any temperature. This is for the complete wavelength from 0 to infinity. But you can calculate the energy emitted by any surface given the temperature here, okay? Therefore, if I know the temperature and I want to find the emission at wavelength of the 10th, I put this equation 10 and calculate how much energy emitted from a black body at the wavelength of the 10th. And C1 and C2 are constant. Okay, therefore these are two constant numbers. We put it here, and we can calculate the emission from a black body. The B here is representing black body at a given wavelength. If I plot this curve, I end up with this curve. Look at here. Here is wavelength. It started from 0.01 all the way to 1,000 micrometer. And here is an energy emitted. This curve didn't come from the sky. This curve came from this expression, okay? Therefore, if I plot that curve and put a different temperature, I can see from, for example, if I have a body at 100 degree Kelvin, okay, this energy comes from that body. If I look at human body, if I look at my body, and I assume is perfect black, this amount of energy emitted from this body, okay? Therefore, this, for example, at this wavelength is that amount of energy. But if I calculate the total area under this curve, the total area on this curve is equal to sigma T to the power 4. total area, it gave me this amount here. Okay, this is the total area from emissivity from 0 to infinity. Okay, therefore here is give you as a function of the wavelength, but if you calculate the total area, give you the total. And when we are defining about the sun, energy coming from the sun, and that last curve representing that one. Therefore, we can assume, okay, we can assume sun is a black body at the temperature of 5,800 Kelvin. Okay, therefore, when we can mention this is the amount, this is a source. The temperature of the sun is more than that, but this is the amount of energy we receive. We can mention this is a source that equivalent of that much energy radiation comes in. And here is, if I integrate from this curve, from this part all the way to this wavelength, I can calculate the total energy come from it. And if I again look at, as I mentioned, we go back to the original figure that we have, I'll just show you here. If you look at here, in this wavelength here, from 0.1 to 100, this is talking about thermal radiation, which include visible, which include ultraviolet, and include infrared, okay? Between this and this one. If I go back, I'm sorry, just pay attention here. If you look at here, 0.1 to that one number, include all of this. Therefore, these are the maximum radiation that we have in that part, okay? This is visible light range that we talk, okay? If you go this direction, related with ultraviolet, and here infrared. Now, something is important, again, we use it all the time when we're trying to design an appropriate material for any application. Look at here, if I connect, these are the maximum amount of the energy emitted at this wavelength. If I come here, if I reduce the temperature to 4,000, this wavelength here giving me the maximum radiation from that one, okay? If I reduce it to 2,000, this point giving you, you can connect this point, all of them, and come up with this expression that we have here is lambda times maximum point equivalent here. This curve represents that part, okay? Something that I'm sure I mentioned in building science, and I'm going to repeat it again. If you look at all those movies, they would like to mention the disasters. They show that the sky is red. Do you remember why? Do you remember those horror movies that you can see, you know, this is the end of the life and the sky becomes red. Why? Do you remember building science? I told you the answer. Wake up, wake up. Are you awake?
Yes, sir, we're awake.
Oh, why is the sky is red?
Is what?
Why the sky is red? And movie they would like to show the disaster. You know, all those movies they would like to show this is the end of the life and the sky is red.
Only a certain type of light is going through.
Okay, this is a question therefore you have to remember. Remember, I'm going to this exam question. Think about it. Look at this graph and tell me the answer. Anyway, this is an exam question. Yes?
It's because of the gas particles, different gas particles in the air. And
this is my exam question. This is a good, you have to pay attention. Think about it. Okay. The variation of exploded body emissive power within this shows, this graph. Several observations can be made. Please look at here. At any specified temperature of the maximum exists. As I mentioned here, maximum, 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 maximum. At any wavelength, the amount of the emitted radiation increases with increasing temperature. If you look at here, 100, when we move to 300, the amount of energy increase. If I move to 500, energy increase. That's exactly the same. As the temperature increased, the curve shifted to the shorter wavelength, okay? As the temperature increases, the curve shifts to shorter wavelength. Look at here, if I go from 100 to 300, the curve shifted to this side. If I go from 500 to 1000, you can see the curve shift to this side. Okay, look at here, the maximum here is at, let's say 50. Here, the maximum is around 0.4. This is something out there. The radiation emitted by the sun is a visible spectrum. That's why look at here. It mentioned this in this range that we can see this. It mentioned this the temperature coming from the sun. it exactly is the maximum, and that's representing the visible range that we can see differently, okay? If we go to this direction, look at if I drop the temperature, look at here, this is the answer to the question. If I go from visible range that it is in this here, if the temperature of the sun dropped from 5,800 to 4,000 degrees, your curve shifted from visible range to red. Therefore, everything becomes red, the sky becomes red. Do you get the answer now? Not yet, okay, think about it. The wavelength at which peak occurs is given by this one. This is called wind displacement law. This chart that I mentioned, connecting all the nodes together, is called this equation. Lambda times T is equal to constant. Therefore, you can calculate, for example, at the temperature of 400 Kelvin, what is the maximum wavelength that you can see, okay? That's an expression. Any question? Now, as I mentioned, in some application, we have to design the system based on our need. Therefore, probably I would like to design, let's say, a solar collector that gave me the maximum energy, absorb the maximum energy. If I have a material in this wavelength, the characteristic of my material, the solid matter in this range, I don't get that much energy. Therefore, I'm trying to select or design this, they work exactly the building science they do. They select, design a material that we can capture the maximum solar radiation. Therefore, they would like to design a system that captures the maximum radiation in this wavelength from here to here. The question here is how much energy we get. And therefore, you have to integrate the area under the curve. Assume you have a material that emit energy emitted by a black body as a function of wavelength and temperature. This represents that one. I can integrate the equation that I had before. Again, let me go back. Again, just remind you, my friend, just let me go back. I can integrate this equation. Look at here, lambda is from 0 to infinity. Therefore, I can integrate this one from 0 to any wavelength that I want. Okay, and calculate how much energy is in that range. Therefore, I can integrate from 0 to lambda 1 and mention this is this one. But I'm interested to calculate the energy between lambda 1 and lambda 2. Okay, but here again, this is, I can integrate. The integration does not have a simple closed form. If you look at that equation that I show you, it does not have any very simple form to give you a number. Therefore, we use a dimensionless, again, indicator. And that dimensionless, we look at how much energy emitted between 0 and any lambda divided by the total, and that gives you the fraction of that energy. Okay, that's fraction of that energy. Therefore, rather than you sit down and integrate between 1 to 100, 1 to 1000, this work has been done and has been given in the form of the table. Therefore, table 2 in your textbook give you the fraction of energy between 0 and that one. If you look at it, I'm talking about this graph, this table, table 12-2, give you the fraction of energy, let's say between 200 micrometer Kelvin. That means here is representing wavelength times temperature. A given wavelength times temperature is 200, and gave you from 0 to 200 is almost 0. Again, if you go to here, wavelength times temperature, if let's see is around 1600, you can see it's less than 0.1% of energy on that one. Therefore, this is the fraction of energy. Okay, this is the fraction of energy. Energy emitted between 0 and lambda, and divided by the total energy. Okay, between the total energy. If you go back and look at here, for example, between this is representing almost 200 lambda times T and 100,000, you can see it's almost 100%. This is started from here for a given body at the temperature T, the total area here is equal 1. It means the total of energy, okay? Remember, this gave you fraction, okay? Fraction, it means how much energy between 0 and lambda 1 divided by the total energy. This gives you the fraction of energy between 0 and lambda 1 at the given temperature. But we can use this table and calculate energy between any wavelength. For example, I have a material at temperature of T, and I want to calculate what portion of energy is between lambda 1 and lambda 2. Therefore, this is representing the emissivity curve that I have, and I would like to know what is the energy, what percentage of energy is between this one and this one, lambda 1 and lambda 2. As you remember, we did it in the class in building science. I calculated what portion of energy is from 0 to lambda 1. I calculate what portion of 0 to lambda 2, subtract them, and this gave you between lambda 1 and lambda 2. Therefore, I use this table twice. I calculate lambda 1 and T, and I calculate lambda 2 and T, and subtract them from together and mention this portion of energy is between wavelength of lambda 1 and lambda 2. As I mentioned, this is very important for us, sometimes because we are designing different material, and we would like to make sure this characteristic of that material is somehow that capture the maximum amount of energy that we have. Okay? Any question? Any question? Wake up. Any question?
No question.
No question. Now I have a question. Have you received your report number 2?
No.
Not yet. Okay. My second question. What is greenhouse gas effect?
The radiation being captured by Earth and not being released because of certain gases in the atmosphere that reflect the radiation from Earth.
Good question. Good, sir. Right, you're in the right track. Why didn't call it blue? Rather than green, why they don't say blue house effect?
Marketing purposes?
Good answer. Why not? I mean, I prefer blue rather than green. Anybody else?
Because a greenhouse is where plants grow and it gets warm with the sun rays. The energy from the solar radiation gets trapped in the greenhouse and it warms up the air.
Excellent. Therefore, you are accepting energy come through the glass, pass through the glass, hit the environment. That's greenhouse. They use it to grow vegetable, right? Am I correct? And then the temperature will increase. As the temperature will increase, unfortunately, the wavelength has been changed. If you would like to visualize it, and this is the radiation come from sun is in this wavelength. Look at here, and then increase the temperature become, let's say, 300 Kelvin. Now you were in this wavelength here, but now that wavelength is become here, and this wavelength is different. Probably the characteristic of the glass, they cannot escape and become trapped inside your greenhouse, and that's why the temperature of the greenhouse will increase. The same thing happened in the environment. From sun, a lot of energy comes, pass it through the atmosphere. Now the atmosphere, because of all this industry and so on, there is a lot of gas in the atmosphere. It covers a wide range of methane, CO2, and name it. And then when passed through the atmosphere, because the wavelength is here, these are short wavelength, they can pass through it. When hits the ground, the temperature of the ground will increase. It increase 40 degrees, 50 degrees, but now they cannot escape because of the greenhouse, because of the gas in the atmosphere. Okay, that's they call it greenhouse gas effect. I'm sure by now you should be an expert because you're building science engineer, therefore you should know that. Let me go back. As I mentioned, now we can calculate exactly what are energy trapped in this two. Let's do this one. Look at here. The sun can be treated as a black body at the effective temperature of this. Determine the rate at which infrared, it means those wavelength in this one, is emitted by sun. Write it down. I will go back and tell me what portion of energy is in the wavelength of 0.76 to 100. Okay, when you finish this part, I can go back. This will come from your textbook. I believe it's problem 37, okay? Therefore, at the end of chapter, probably you have the textbook, you can see. How can we solve this problem?
We find the
Do it, please.
the
Do it on the
amount.
paper.
Oh,
Do it
okay,
on the
okay.
paper, please.
Sir, your mic is off.
As I said, I'm going off now. I'm not around. Remember, the temperature is given ranking, okay? Is not, make sure that when you're using through this table, this is Kelvin, okay? Therefore, it mentioned in the wavelength of 0.76 and 100 micrometer. It mentions temperature is 10,400 ranking. You can change it to Kelvin, and then you calculate your, you can calculate your lambda 1 T, 0.76 times the temperature in Kelvin again, remember, and you can find out here in which number it is. You can find what portion of energy that falls from 0 to lambda 1. And the same thing you can calculate for the upper layer. That means 100 micrometer. And you can go back and calculate what range falls, and you can calculate your, this one, lambda phi2. Therefore, T, the temperature is the sun, is the same both case. This is your 0.76, this is 100. And you can calculate what portion of energy falls in this range, okay? Okay, so let me go ahead slowly. Therefore, this is equivalent to 5778 Kelvin. Therefore, your temperature in Kelvin is this one. And you know what's lambda 1, 0.76. You know what is lambda 2. It means 100. Therefore, you calculate lambda 1 T and lambda 2 T, and you go to table 212. Therefore, lambda 1 T, if you multiply, become 74391. Okay, let me go back and show you. Remember 4391. We go down here. This is 439. Therefore, there is something in between these two, and you can read this number in between. Okay, practice it, please. Again, here is this one, 4391, that number, and you calculate lambda 2T, the lambda is 100 micrometer, temperature is this one, and this, look at here, this becomes this number, 577800. If you would like to go back, I'm sorry, again, let me go back here and end up some places around this number, okay? Therefore, it is almost 1, okay? Therefore, now it tells you if from here to here is around 0.5, around here to here is around 1%. Therefore, the difference between these two is a portion. This is from 0 to lambda 1, as mentioned, 0.4 something. And from 0 to lambda 2, we mentioned is around 1. Therefore, if subtract these two, give me the portion of the energy falls between these two wavelengths. And that exactly we did here. Okay, this is 0.4 from 0 to this one. This is 1 from 0 to this. Therefore, if I subtract it, this gave you that one. It's around 0.43%. What that means? It means 45% of the total energy falls in that range. How do you calculate the total energy now? If you would like to calculate in watt, what do you do it? If you would like to calculate watt per square meter, how much energy it is?
We times it by the temperature to the 4 and the
Sigma.
sigma, yes.
That's right. As I mentioned, this is the percentage. That represents that percentage over the total. The total is sigma T to power 4. Therefore, we can calculate how much energy. Okay. Now, let's look at this temp. This is an example, or if you would like to look at it. Yes, sir.
The temperature we're going to use to find the energy, is it the sun's temperature or the temperature that is currently?
This is the source. This is your source. You're trying to calculate what portion of energy emitted by sun. Therefore, this is the temperature of the sun. This exactly falls.
So
in
the
this
T, we use the 5,778,
yes.
right? Okay.
As I mentioned here, we're trying to look at what portion of energy from sun end up between these two. If we go back here, is this can be considered a black body at this temperature. From this source, this is the one that you have. You would like to see what rate of energy falls in this. Therefore, yes, the temperature consists sigma to power 4 is this one. Did I answer your question, sir?
Yes, sir.
Yep. Okay. Now you can calculate this one to see how much energy it is. Okay. That we calculated, and here, therefore, if you multiply this one by sigma T to power 4, gives you the amount of the energy falls between these two wavelengths. Now we go a little bit further. Now we would like to get involved in the design. And in order to do that, we have to understand what exactly how much energy received. Therefore, we use a term called radiation intensity. If you look at here, this is a source that I have some radiation comes in, or assume this is my source, some radiation goes out, okay? Therefore, this is emitted radiation from that source that I have. I have a point here, delta A, this is my portion of that surface emitting some energy. As I mentioned, this is like a sphere emitted in all directions, okay? As I mentioned, diffuse in all directions uniformly, okay? That's an assumption that we are making. It's a fused surface and emitted uniformly in all directions. And for this, I can refer it, this is the ray of radiation comes at this angle, azimuth here, and theta here. This represented this as function of this two angle that I have, okay? Therefore, the direction of radiation passing through a point is best described in spherical coordinate. Remember, I mentioned diffused, emitted in all directions. Therefore, if you consider all direction, it's become almost hemispherical coordinate. Okay. Therefore, that's something we have to keep in mind. And we can specify by knowing that these two angles, theta, zenith angle, and azimuth angle. Okay. This angle and this angle. Okay. Therefore, we can represent this one. Radiation intensity used to describe how much emitted energy varies with these two angles. Okay. Therefore, if I change this one, we can calculate how much energy comes. If differential a small surface in space, okay, this is the cone is coming here, it's coming uniformly, this angle here, through which the radiation passes substance is solid angle. Therefore, the terminology we are using, we call it that solid angle. The omega, that's exactly represent this part. And we can review this that dA that here. This is the source energy emitted, these two angles, and now we have a solid angle that we can describe. The solid angle is described as this one, ds over r2. Okay. If we look at here, this is the surface that you have, energy emitted uniformly in all direction. Okay, all direction. Therefore, your theta angle goes from 0 to pi 2 here, right here. Okay. And this theta is going to pi. Okay, so this angle is all direction that you have. This is theta that you have here, and this theta is from 0 to pi over 2. Okay, there's a differential solid angle, the W that we mentioned here. It can be described by this expression. Therefore, here we can represent this one as ds here, and can be defined by knowing those angles that we mentioned. Again, this figure in your textbook exactly represent what that means. That this one magnified here is r theta. This is your r, and that the theta is the angle that you have right here, and this angle and all. Therefore, we can specify that's ds as function of r and these two angles that we have here. And this we call it solid angle, and that's the s over the earth. Therefore, this is a little bit geometric. In a spherical coordinate, we're trying to define how much energy will coming out of that surface to a given angle.
Sure.
Yes, sir.
Go ahead. That's fine.
Therefore, here, the energy intensity we mentioned here as a function of these two angles, azimuth and zenith angle, the total radiation comes here divided by the solid angle. Okay, that's the define here. And if you would like to calculate, yes, sir.
What's SR? What's the unit? SR? The unit?
SR.
It's watt per meter squared per SR.
This SR?
We can see your mouse, so.
Yeah, we can't see your mouse.
The SR at the bottom
Yep.
corner.
Yes, this one, this.
It's a unit of angle. We get to that part shortly. Just again, we are talking about per unit angle, per unit surface, and that's exactly representing. Okay. We get to that part shortly. Okay.
Okay.
We mentioned here before. We mentioned energy emitted per unit wavelength. Now we are talking about energy emitted per surface area per unit angle.
Okay.
Now, if you can integrate those energy, as I mentioned, if you go back here, we integrate the energy between this angle, look at here, from 0 to pi over 2, and from this angle to here, pi, 2 pi. Okay, if you do that one, we get the total energy emitted by the surface. And now, since we're covering the complete range of the angle, now give us watt per square meter. It's not a function of unit angle. Okay, this is the total energy emitted by the surface. But in your application that we are assuming is constant, it's not a function. for some material, these are the functional angle. But for the case that we are assuming ideal black body, and it's not a function of angle of theta or phi. Okay, that's exactly the whole idea simplification that we are making in our calculation. Okay, therefore, for our case, these is constant. You can take it out, and if you integrate this per unit angle and so on, we end up become like this. Therefore, energy emitted is equal to pi times energy intensity. And for diffuse system, this value is constant. It's not a function of phi and theta. Okay. Therefore, we can calculate easily.
Can you go back, sir, for 1 second? Sorry.
Yes.
Good, thank you.
Okay. Therefore, we can calculate now the energy intensity because we know the total energy has been emitted. And therefore, here it gave us per unit of angle. Okay. Just for your information, let's go back. If you have your textbook, please open your textbook. If you have it, if you bought it, if you know it. I would like to show you where it is. Chapter 12. These are, we are covering those equations that mentioned. These are, I have the equation number here. Academic textbook did not give you an equation number. Yeah, it is. Okay. Therefore, we are covering the part that mentioned this 12.4, chapter section 12.4 to 12.5. Okay, these are the section is referring to that part, that calculation of diffusivity and also intensity. Okay. These are only covering that part because this is, again, you come back to material that we are dealing is the idea here is in some material, real material, the energy emitted from the surface is a function of those two angles. But in our calculation, we always assume independent and uniform in all directions. Okay. Now, just to do it, I have one more example to do it. Please read it and tell me how we can do it. Okay. The emissivity of tungsten filament can be approximated to be 0.5 emissivity for radiation at wavelength of less than 1 micrometer and 0.15 for radiation at a greater range. Therefore, if I want like to plot it, emissivity is a function of the wavelength. If it's in this range, the value is 0.5, and more than that is in this range. Determine the average emissivity of filament at 200 degrees. Again, write this down and let's do it, and then we can discuss it next lecture, because I would like to have a clear understanding of the subject. Okay? I have the solution, but I prefer you spend some time to understand. Therefore, let me go back again. We mentioned that we have a source that emitting energy, and we are trying to find what portion of energy emitted from this surface. The idea here is trying for you to understand this is a spherical coordinate, because we mentioned if energy comes from all directions uniformly at this moment, but for some material is depend on angle. Okay, to come with this, what we define here is a spherical coordinate, and each radiation comes from the surface is a function of these two angles. Okay, at the end we are going to make an assumption for our application in building engineering, but in reality this ray is coming here is a function of these two angles. As I mentioned, radiation described the radiation varies with these two angles in real material. Any material, if you can't believe, I'm sure in textbook there are some material that show that this ray is changing as a function, as emissivity change, as emissivity becomes function of these two angles, transmissivity becomes function of this two angles, and so on. And we define a solid angle, because here this is surface, a small angle that we come here. This is total energy emitted, but as move direction, slowly expand, and that we're trying to find what is called solid angle. Okay. Differential is small surface in the space, this one, through which radiation pass through, is called solid angle. And you can see this will change as the function always going in that direction. We define this solid angle here. The solid angle is ds over r squared. That represents, this is the r here. This ds represent, this is the area that energy emitted, and function of r. As r change, the area is change. Okay. Okay. Therefore, we can calculate this solid angle, the w, based on that one, as a function of r. As I mentioned here, now if you would like to calculate the total, we integrated this one for the total of, as of this is energy. Let me check in. I'm sorry, repeat it again. This intensity is a function of these two angles. Okay, therefore this the total energy comes out divided by this angle. As you mentioned, based on what per unit area. And styrene is called the angle for ds. Okay, therefore this we call it solid angle that we have here. You can have a unit of this. If you look at here, this is the unit angle we have here. It's called styrene per unit angle. Per unit angle. If I integrate it for the whole surface area, this will appear. Call it styrene, and that's what we have. Now we can calculate the total area per unit area, and that we divide this one. We call it flux because it's per unit area. And if I integrate it from 0 to pi 2 and 0 from 2 pi, the total, I can calculate the total radiation comes as a function of these two angles that I have. Okay. But if I assume it's diffuse, again, remember, if I assume it's diffuse, it means uniform. It is not a function of these two. This is not a function of, this is the definition mathematic. it is not a function of this, it's not a function of this. This value is constant. It means in every direction is the same. Therefore, I can take this one out of here, and if I integrate this value from this one to from this to pi over 2 and 0 to power 2, I end up with this expression. Okay. This expression is constant. I can take it out right here. And if I go one step further, I can calculate the energy emitted as a function of intensity. Therefore, this is something that we should remember. Therefore, now we have the total energy emitted by a black body. If I want to find the intensity divided by pi, okay? This is per unit of solid angle, okay? I come back to this one later on. Now we go back to look at the physical property of the material when we are dealing with the energy storage, when we're talking with the conductivity, we are dealing with certain, but many material encountered in practice, such as metal, wood, brick, are opaque. Okay, therefore now we are talking about what are the physical property. What is opaque? It means the transmissivity of the material is 0. No energy will pass through it, okay, to thermal radiation. And radiation is considered to be a surface phenomenon, okay. In this material, the thermal radiation is emitted or absorbed within the first few micrometers. Therefore, energy, when reach the surface area, will not penetrate. It's only at the surface level. Micrometer will be absorbed, okay? And the rest either be reflected or emitted, okay? Some material like glass and water exhibit different behavior. We call it visible infrared. Therefore, it's portion of energy can pass, portion can be opaque, okay? Therefore, we have to look at when we are dealing with different material, we have to find out what exactly the characteristic. When we are talking about the solid, it's only about a few micrometer in the surface, micrometer, okay? And the rest will not penetrate. But we are talking about the gas, again, gas depends what concentration we're talking. If I'm talking about the environment, I can assume is transparent, it pass through. But when I'm trying to design a furnace that I'm dealing with a lot of smoke, I cannot assume is transparent. Some of the radiation coming from the fire will be absorbed by the gas, okay? Therefore, we depend on the application that we have to keep in mind what are the characteristic of that. Therefore, in outside air, when I assume radiation comes, I ignore all the characteristic of the gas in the atmosphere. But when I'm designing a boiler that use wood and so on, there is a lot of smoke. Some of those energy will be absorbed by the gases, okay? Now, when we come back, emissivity. What is emissivity? What is transmissivity? What is reflectivity? Emissivity of a surface is the ratio of radiation emitted by the surface at a given temperature. Remember, to radiation emitted by a black body at the same temperature. Therefore, now we can consider slowly, as emissivity is also a function of the temperature, and also emissivity is a function of wavelength. Therefore, when we define emissivity, is both as a function of the temperature, because energy emitted is a function of wavelength. I'm interested about a specific emissivity at given wavelength, or I'm talking about total emissivity. Okay. Therefore, if I'm talking about the general emissivity, is a function of the temperature. Therefore, here emissivity is a ratio of radiation emitted by the surface at a given temperature to that emitted temperature of a black body. Therefore, my reference body here is black body. I look at here is how much energy emitted from that black body. I measure how much emitted from my surface. The ratio of these two represent emissivity. Therefore, since they're talking ratio, emissivity maximum could be 1, because ratio is maximum 1. Therefore, emissivity is between 0 and 1. Therefore, emissivity is denoted by epsilon here, and is between 0 and 1. The emissivity of real surface vary as a function of the temperature, as I mentioned, wavelength, as I mentioned, direction mentioned. In real material that we are dealing, we are assuming the emissivity is a function of the temperature, function of the wavelength, function of the direction. But in most of the problem that we are doing at the level of the building and the range of the temperature we are talking, we can assume emissivity is constant, okay? But please keep in mind, When you're there going to working with NASA, you cannot assume this one. You're in NASA, you have to consider this is emissivity change. When the space shuttle entered the atmosphere, you cannot assume it's constant. It's changing. Okay. And for here, we have to keep in mind. For some application, we can assume it's constant. For some other application, we have to take into consideration. A spectral direction emissivity is the most elemental emissivity of the surface at a given time. Therefore, when we're dealing with material, we're looking at this emissivity. Okay, we are looking at average emissivity of the system. Therefore, emissivity, as we define in real life, is a function of wavelength, direction, and temperature. This is in real material we are dealing. In general application. Okay, therefore these are emitted from the body, that the surface that we are dealing, as a function here, to the black body. This ratio called emissivity. Therefore, emissivity is a ratio of two. How much energy emitted from the surface? I am interested to my reference one, black body. The subscript lambda and theta are used to designate a spectral and direction. Okay. Therefore, these are we're preparing for a given wavelength for a given angle. As I mentioned here, when we come back at the end, here, this is different. If I assume it's not a function of theta, we can simplify this expression only here. It's only a function of temperature, and temperature is not a function of angle. If it's diffuse emissivity in all directions. Okay. Therefore, keep in mind what is the definition and what problem that you are going to deal in the future. Even when it comes to a building application, we ignore as a function of the wavelength. Okay, we assume it's constant all the time. Okay, therefore here we assume here the one we are using in our calculation, we always assume emissivity is constant and is on here. Okay, therefore keep in mind that exactly what is the definition and what exactly we are trying to solve. Okay. Therefore, here is the total energy emission from the surface as a function of the temperature and lambda divided by to my black body, and therefore we can define this emissivity. Okay, let me see if I have a graph. Look at here, this is exactly what I'm trying to tell. If you look at the conductor here, your emissivity is a function of the theta. If non-conductive material to behave like this, therefore it's a function of the angle of incidence. Okay. If I'm looking at this body here, for black body, we assume is constant all the time. But the gray surface, that the material that me and you are doing building engineering, we can assume it's changing like this. Therefore, we can add, we take an average. Okay, we assume it's not a function of any more temp lambda, as we can assume it's constant almost. Therefore, the number that you can see in the table that's given here is an average we're taking. But in reality, is changing as a function of lambda. Look at this material again. This is the black body. We assume it behave like this, but in reality, emissivity coming from the material is changed like this. Is the temperature function of this one. Okay. Therefore, the number that you have in the table is an average for the given application that we have. Again, we are dealing thermal radiation, and we are dealing with given a certain range of wavelength. We are talking about 0.4 to 1, okay? We're not talking from 0 to infinity. Therefore, for some art here is diffuse radiation surface, which properties independent of the direction. Gray surface is properties independent of wavelength, okay? Therefore, this terminology also remember. Diffuse, it means radiation in all directions are the same. When we're talking about gray, it means independent of the wavelength, okay? Therefore, here is gray that we are discussing, okay? Therefore, please remember again, what you should know, this is a real scenario. Your emissivity is a function of lambda, temperature, and direction that you have here, okay? In real application. But when we are trying to deal with the problem that in building engineering, we can assume it most of the time is diffuse, independent of direction. And if you look at here, again, these are normal that come from your, here is represent spectral normal emissivity, okay, spectral, remember the term, and look at here, behavior as a function of wavelength, Look at here, this again, we're talking total emissivity is a function of the temperature. Again, the work we are doing mainly in a small range of here is right here. Okay, most of the thing we can assume is almost constant. If you look at here again, for this one, shows the emissivity of different material as a function. Any question, please? Any question? Are you still awake?
Yes, sir.
Good. It seems the copy is working. Now we define emissivity. Therefore, emissivity, we define the amount of energy emitted by a real body to amount of energy emitted by a black body. That's why we define emissivity. But there are some other parameters that affect the radiation. If you look at the surface, a certain radiation comes here, portion will pass through it, portion will be reflected, portion will be absorbed. Remember, I'm saying portion. It means a ratio of it, okay? Therefore, we can define what is absorptive material, the energy absorbed by the material to total. Therefore, here is the definition of absorptive. Therefore, this have a meaning again. Remember, we mentioned absorptive. What that means, absorptive? It means the ratio energy absorbed by the material to the total energy comes to the surface. We call it incident radiation. Reflectivity, what that means here is rho. It means rho here. It means the portion of energy has been reflected from the surface. Reflected is different from emitted, my friend. Reflected from the surface to the total comes to the surface. Again, transmissivity, what portion of energy transmitted through the material to the total comes here. Therefore, these have meaning, okay? Alpha, rho, and tau. When you select a window, you would like to transmit it. You can transmit as much light as possible because you would like to see outside, okay? In some cases, for solar collector, when we're dealing with central system that we for solar energy that we collect, we would like to have much reflectivity in order to reflect it to the storage to store energy, okay? In solar collector, we put it in roof of the building. You would like to absorb maximum solar energy. Therefore, you select your material at highest absorbability because that you would like to increase your amount of energy received, those photocells and so on, okay? Therefore, depend on the application that we have, you would like to. These days, we are talking about climate change. We are talking about greenhouse gas emission, and we are talking about cool material. Remember, my friend, cool material. What that means, cool material. Have you heard about cool material?
Nope.
No? You should, because you have done the project number 1 and 2. At least I was hoping somebody mentioned about cool material. The cool material here is absorb minimum amount of radiation and reflect most of them. Therefore, they are using now white color to color the building, okay? Paint it white because to reflect maximum energy to outside. It doesn't absorb energy in the community, okay? Therefore, we call it cool material because those material has high reflectivity because reflected back to the sky, okay? Therefore, these are something we have to pay attention. Okay. Here is called cool material. If you just Google the cool material, you can see material has high reflectivity that reflect back maximum radiation. Okay, therefore down to now, if I write, I said a certain amount of energy comes here, G, that portion will be reflected, that portion will be absorbed, that portion will be transmitted. If I write a simple energy balance for this surface here, a simple energy balance for here, I can see a relationship between this variable, rho, alpha, and T, okay? And that's exactly here. If I said portion absorbed, portion reflected, portion transmitted, it is equal to total energy comes here. Therefore, we have this relationship between these properties. Therefore, absorbability of the material plus reflectivity of material plus transmissivity of equal 1, okay? Therefore, if you have 2 of them, you can calculate the third one. For opaque material like concrete, brick, and so on, transmissivity is 0. Okay, that's exactly the makhas. Therefore, if you're trying to look at a window, the summation of absorbability and transmissivity equal 1. Okay, a portion of energy will be absorbed on the surface of the glass and portion will pass. Okay, therefore I will stop here because my time is over, my friend. If you have any question, please do ask. Therefore, if I go look at the class, please, almost finishing chapter, not finishing, it's still on chapter 12. Remember, I jumped 10 and 11. We are in chapter 12, radiation. And the first few section is discussing an overview of building science that you have. Please read it. As I will start to do more problem, at least be able to understand. Okay. Any question you may have, my friend? I will be here another 5-10 minutes. If you have any question, please do ask.
Sir, do you mind explain me the table at the beginning of the class?
I have no problem to explain you, sir. Let me go to the table, sir. You're talking about this table, right?
Yes. So for the example, we are giving the range.
Let me show you first, explain you the application.
Okay.
Application, when I try to, you have heard of a solar collector, right?
Yes.
Therefore, we use solar collector to heat the building by passing air through the solar collector. We're using solar collector to heat water for the sun. Therefore, in order to do that, we have a material that absorb. We're trying to maximum radiation. Okay, solar radiation comes here, increase the temperature here, and then air pass behind it into that. Now, the amount of the radiation comes is a function of wavelength. Okay, therefore, if I'm a material scientist, I'm trying to select a material here to have absorb maximum radiation. Therefore, maximum radiation, if I go back to a slide I had it before, you can see the maximum radiation is in this range. Look at here, this is the maximum radiation that we see. Therefore, I'm trying to design my material that absorb the maximum radiation. Therefore, it only absorbs radiation in the range of, let's say, 0.4 to 0.7, okay? Now, the question here is how much energy I'm going to absorb on that one. Therefore, what I do here, I need to calculate how much energy I'm going to absorb. Therefore, I would like to calculate how much energy I absorb between 0.7 to 1. Therefore, I have to integrate that equation that I have here. I have to integrate here, look at here, this gave me amount of energy emitted by surface between at a given lambda. Therefore, I have to integrate this equation between lambda 1 and lambda 2 to tell me how much energy I receive in these two range, okay? In these two range. And trying to integrate that equation is very difficult. And trying to integrate that equation becomes difficult. Therefore, what they did, they make it simple. Rather than asking you to integrate, they did an integration and they gave it as a function of percentage. What percentage of energy is between lambda 0 and lambda 1? And what percent of energy from 0? Because always they integrated from 0, from here. And then subtract this one. Therefore, here, this graph, this table gives you the what portion of energy is between 0 and any wavelength that you like. Therefore, lambda 1, T1, you calculate lambda 1 here, and you find an appropriate number, and that show you, for example, if it's 2000, it gave you only 6% of 0.6% of energy on that between this number. Did
Yeah.
I?
Yeah, I think I understand now.
Good.
Perfect. Thank you.
No problem, sir. Any further question, ladies and gentlemen? Ask any question